Swayam Prabha. Digital India. Educated India.
In the last class we have seen how we are in the last class we have seen that what is the basically meaning of the orthogonality, how different mode shapes we can get, and what is the understanding of an orthogonal system once we are converting a system or break a multi-degree freedom system into several equations. Then we have seen that how we are getting from a single means from a 2-degree freedom system, how we can able to get two uncoupled single degree freedom system, from where by combining their responses we can able to trace back the response of the main system. That we have seen in the last class. Like we derived all the expressions and all those things and we came up with that. If you see in the last case we have derived that also. What is the mass normalized mode shape? Because orthogonality relationship tells that if we are taking the two eigenvectors, then they are orthogonal, and orthogonal means if we are doing like phi r transpose phi k, we should get it 0, and if we are doing phi r transpose m phi r, we should get some value. Okay, and that value may be 1, may not be 1, depending on the phi. If to ensure that this value will be 1, like for example you can see here, that is phi r transpose m phi r, that is equal to m r bar. Okay, so it's giving some value, but now we try to ensure that this value should be 1. So then what we should do, we should, because we cannot scale the M matrix is the mass matrix, that's a constant value, so we can alter this phi r and phi r. Obviously phi r, if we are altering, phi r transpose will automatically be altered. So what we are doing, we are just dividing that with the root over of m. So if we are doing it with the root over of m, so that means we are dividing it by that, means once they are multiplying also, then it is totally m r bar, and from that m r bar we can able to say that these two things will become 1. So that was the basic understanding of this way, because phi is such a type of vector which is nothing but a scaling. It's a still that what is the ratio from one to another to another, so that it's a scaling type thing. It is not at all a specific values, they are not displacement, they are mode shapes. So that thing can be scaled, but it should be scaled uniformly, so that like all the values are scaling properly. Okay, so therefore we can able to use this MR bar concept. And as I was telling, that if you use the mass normalized eigenvectors, then in your reduced system always your mass will be remain 1 and stiffness will be a frequency square. Okay, whereas if you are not using the mass normalized, then it will have some mass, and obviously that mass into frequency square will be the stiffness. Okay, so this is nothing but the scaled system. Okay, makes sense. And we have also discussed like how we can able to visualize that, like the stiffness is weakening and we are rotating our system and we are going into a particular axis which is the eigen axis, and from there we can able to looking at the full space, so that we will get the equations. And then we have also shown like in the transfer system it can be coming, and this is the modal participation factor. We have discussed up to that stage in the last class. So that is the modal participation factor for the rth mode. So rth mode means we can say rth single degree freedom system also. because each mode is corresponding to one single degree freedom system. Like first mode is corresponding to this, second mode is this, third mode is this, like this. Okay, so once we are telling that rth mode, that's corresponding to one single degree freedom system. Okay, and this is the participation factor. That means if we are applying the forces like F1, F2, F3, F4 like this way, then we need to also identify how much force is coming here, how much force is coming here, how much force is coming here. That we have to also identify, because they will be not same. This gamma 1 does not represent F1 directly, because this is another rotating frame of axis. So we have to also identify that how much force is coming onto that. So that procedure is that, like, so this participation factor actually tells us what is the participation of those forces into that single degree freedom. Means, or you can say that how much force, means this single degree freedom can be excited by some force. So what should be the magnitude of that force, so that you can able to add them up as we did in the last class. Like you can see, like once we have done the full solution, you see like each system, like we have the Q1, we have the Q2, and our total response is 5(1) times Q1 into 5(2) times Q2. So the similar manner, this equation and this equation was a free vibration equation. You may have a force vibration equation also. So if you have that gamma r, then you are having a, instead of a zero term, you will have a force term. So those are like a forcing function is will be applied on that. So you will be able to see some oscillations also. So modal participation factor represents what is the amount of the force acting on that particular model, or like correspondingly to that mode, whatever the single degree freedom system is there, how much force is going to apply on that. So that is the meaning of the modal participation factor. Okay, don't get confused with that 90%, 95% clause of the Indian code. That is not with the modal participation factor, because once you will solve, you may found some cases modal participation factor could be negative also. Because for example, if I just show the example, like if you see in the last class, once we have find our 5 matrices, you see that this matrix is a negative matrix fully. Okay, so now if you placed it here, phi r, that full thing is negative, no problem. F is a positive number, mr is mass, so that will be automatically positive number. So your full phi r, gamma r will become a negative value. Agreed? So do not get confused it with the 90% clause, because there none of the thing can be negative, that all the things are adding up. Because, and why it is negative can be possible here, you may have the force in the other direction. The force may be applied in a 180 degree phase, so that you can able to get positive, negative, all those things are possible. Okay, so now let's see what is that 90 or 95% clause in Indian code. That is known as the mass participation factor, not modal participation factor. There's a very small difference, but they are different. Okay, so mass participation factor, and this one, sorry, and this one is the modal participation factor. Okay, so once we are talking about the mass participation factor, in that case we are saying that mass participation factor is Okay, that is the mass participation factor. Now mass participation factor is mostly used for the earthquake case only. Okay, let me show you how it comes actually. And okay, so first like see what it is here. So phi r transpose m r. Okay, that is not phi r, that is only m r, m into capital m into r, and that is phi r transpose m phi r. So phi r transpose m phi r means m r bar, no doubt. We automatically see that. So that is the mass of that mode. Correspondingly mode is that mr. And what is that? Phi r transpose mr whole square. So here that r is a different thing, that is not at all coming from phi r. That r is telling how the forces are coming in each mass due to the uniform base excitation. Okay, I will derive that portion also. And mass is the mass matrix and phi r transpose is the thing. Okay, is the model, is the mode shapes. So if we see that how this thing happens, so let's assume like we are having a system which is getting base excitation. So base excitation means we are like moving it with the UG double dot ground one. Okay, so you will find it like maybe starting from here x1, x2, x3 dot 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 xn can be possible. I'm not writing it. So how its equation should be happened? So we can say that m1, and this is mass is m1, m2, m3, k1, k2, k3. So m1 x1 double dot plus c1 x1 dot, or maybe I'm just leaving the c first now. Just assume first we are doing it for the undamped case. Then we will see like how the damping will be coming into picture. Okay, so then the k into x1 minus, yeah, so if you see there is a two coordinate can be possible. One is, if you remember one of our discussion where we did for this case, just like we have a single mass and we showed that okay, if it is having some sort of ground displacement, how the solution should be. So we showed that in that case mx double dot plus m into x minus ug, not m, k into m minus ug, that is equal to 0, because we are having a base excitation. Okay, so now we changed it, x minus ug should be z, that is the relative coordinate system. Means suppose if some person is standing here, so the base point, how the top mass is moving with respect to the base point, so that is the z, so that is the relative. So now if I just do it like x double dot minus ug double dot, that will be z double dot. So if I just substitute x double dot equal to z double dot plus ug double dot, so I will get m z double dot minus or plus m ug double dot plus k into z, that is equal to 0. So m z double dot equal plus kz, that is equal to m into ug double dot with a minus sign. So that type of equation is for once we are talking about relative movement, and the case is the base excitation case. Okay, so here rather I should use the z. So also you can write x, not a problem. So if you are writing x, then we should use here this and 0, and others will be remain more or less similar. K into x2 minus x1, not at all, that is plus k into x2 minus x3, that will be 0. Here also something will be having, sorry, plus k into x1 minus x2, that will be 0. Okay, so like this way your equations will come in. Okay, so this is if you are writing in terms of x coordinate, or if you are writing in terms of z coordinate, then we can as we have seen here, it will be m1 z1 double dot plus k into z1 sorry k1 into k1 into z1 plus k2 into z1 minus z2, that will be equal to minus m1 ug double dot. Okay, because x1 minus x2 will not be changed anything. Why? How it will be? x1 minus ug will be z1 and x2 minus ug will be z2. So if we just subtract these two, x1 minus x2, ug will be cancelled out, z1 minus z2. Okay. So once we are just subtracting the two coordinate, whether they are in the absolute or whether they are in the relative, they were not affected. They will be remain same because we are subtracting a same number. Okay. So then next case will be m2 z2 double dot plus k2 z2 minus z3 z2 minus z1 plus k3 into z2 minus z3, that will be equal to minus m2 ug double dot. Make sense? So this way your things are coming. So if you are putting it in the matrix form, m1 m2 whatever is coming with z1 double dot z2 double dot z3 double dot like this plus k1 plus k2 minus k2 minus k2 k2 plus k3 minus k3 minus k3 k3 plus k4, whatever, if it is coming at all. So like this way this thing will go, and z1 z2 z3 so on equal to, important point, minus, that is equal to is already there, minus m1 m2 m3 like this into, that is the point, into ug double dot. But if you see matrix wise, you cannot multiply this way because this is n cross n and this is 1 cross 1. How will you multiply? If it is identity matrix also, it will not help you. It's a once, yeah. So all the thing can be 1. That is okay. So this is known as R. That R, what I used here, if you remember, that R, that is phi R transpose M R. That R is this thing. That one vector. It is like a completely 1. Okay. Makes sense? Now, if this is the one, it is done. So what are we getting here? This is my M matrix, K matrix, Z matrix, yes, and this is. So this is R, and from here we can able to calculate the dynamic mass participation factor. There, actually, what we have to do, once we are getting that mass participation factor, then we have to check that whether that is within 90% limit or not. Here there are two things. If you are using the orthonormal modes, that means you are using the mode shape after doing the mass, that is the mass normalization, then, and if you are using that mode shape, then this formula is sufficient to calculate because your bottom will be 1. So from the top you will get whatever is coming. If you are also not using, it will be coming, and but there actually one term will be remained. because you will have some amount of mass left, so that square will be there. So then again you have to divide it by the total mass, and then you have to check whether it is coming to what is the value it is coming. Okay, so this ratio means some of the cases you may just see m like whatever is coming here, that is the mass participation. So if I just say me, so me divided by total mass should be have some value. So like this way, that is for first mode, second mode, third mode you are doing. So if you just add that me2 by total plus me3 by total, that should be less than some value like 0.95 or something. Sorry, that should be greater than 0.95. So in those cases you can say that okay, now that many number of modes is sufficiently giving you the result. Means you need no more values, because there may be like a slight variation. If you think that aspect from some sort of real life approach, like for example, you try to find out a position, a place. Okay, you want to go there, you want to navigate there, and you try to finding it out. Like let's say some people is living outside the India, and he want to visit IIT. Okay, how he or she will come? So they will first come to Delhi. So that is the means they will first find it out that okay, Delhi is in India. That's first step. Then like okay, this location is Delhi, so they may come to airport. Then they start finding out that okay, nearby location to go, like maybe there is some landmark. So they try to see that okay, this is in the Hotchkiss area. So they go to the Hotchkiss area. In Hotchkiss area, where is IIT Delhi? They come to IIT Delhi first, and then maybe particular department, they will go to that department. So this way you are actually searching. Here also first mode is something like you are reached to India. So that tells the bigger picture. Then second mode is like you reach to Delhi. That's the second one. Third case, you reach to IIT Delhi. Fourth case, you reach to department. Then maybe fifth case, you are finding okay, which number of stair. These all the small details are coming into there. So this way you can think that each modes are actually contributing to the higher or finer informations as much as you are going on. Now you can find it out that okay, once you are solving, like if you reach to IIT Delhi, whether that is sufficient or not. You maybe don't need that okay, how many stairs I have to climb to reach that particular room. That's also not required. Maybe you can say that okay, I will find it out once I reach there. You don't need to solve it through that full mathematics, or maybe that much of finer requirement is not there. Like once we are mostly the civil engineering case, if you are looking, we are using some good factor of safeties. So some of the cases that factor of safety will take care that okay, that small details we don't need to at all bothered. So like this way you can, means I just give it as an example just to make your mind clear that okay, what is the level of approximation is these things are actually doing. So you can see that for normal structures, if you see the first mode, that will mostly contribute around 75% or 76%. So like you mostly done. Then second mode, if you just add on top of it, it will be also means second mode is mostly contributing somewhat 15%. So 75 plus 15, almost 90% is covered. Third mode, maybe you can see again 5 or 6%. So your 90% clause mostly completed. Some of the cases that not happens, like for example, if you are going to check for the dam case, if you do, means that was my MTech topic also. So I saw that like empty reservoir case or like a normal with reservoir, whatever you do with fluid, means with soil and all those, first mode goes maximum 50%. So that creates a lot of problem. Now first mode did not reach to that point. Means suppose you instead of finding it India, Now you are saying, okay, it can be Indian subcontinent, India, Pakistan, China, all those things are coming into the point, and now you are searching it. So your first approximation itself become quite blurry. So that's some type of problematic thing happens. So then you need maybe 10, 12 modes to go to see that, okay, that 95% is coming. Because if you see the dam structure compared to a my building structure, they are fundamentally very much different, because that is mostly a continuous structure. Like you have full mass of concrete throughout the body. Masses are mostly predefined. That can also create some problem in case of building if you put some portion suddenly a heavy equipment or something, which are mostly fixed. Because if there is a fixed equipment type thing, you have to consider that in the model, because once earthquake happen, you are not removing that machinery. So that also need to be considered in the seismic mass. So in those cases, you may found suddenly the 2 or 3 mode may be coming very close together, and that can also disrupt the full thing. So that is why if you see in recent version of the 1893, like in the 2016 version, there is a clause added that is a mass irregularity. Like if you are going for the horizontal, means the vertical mass irregularity is one of the big important point, because that sometime kills this type of nice participation factor. Like if you take a normal building, three to 5 modes are mostly sufficiently you will reach there. But yeah, if there is some sort of irregularity or some of the things are there, it will not going to cover it. Maybe then you need 20 mode or something, means it will become like a dam analysis, like you have to do all those things. Okay, now let's see an interesting matter, that is, suppose, like what we were just discussing, suppose we are not considering all the modes. That means what are we actually doing mathematically? Okay, because obviously, suppose you are having like a, we just let's go from the 2-degree freedom, because mode degree of freedom is very difficult to understand. If we can understand 2-degree of freedom, we can do it for other degree of freedom also, hopefully. So just let's say we have a system like this. Okay, that is M1, M2, K1, K2. Okay, so we, or maybe we can just go back to the our previous case actually. Yes, so that was my equation. I think so. That is like a 50, 5, 0. I think that is 150. So that was my first system. Okay, now I try to see that, and once we do the modal analysis, what are the modes? So modal analysis, yeah, so we got it 8.8 and 37.8. Okay, 8.8 and 37.8. So we are getting two frequencies, 8.8 and 37.8. Good. And what is the mode shifts? Minus 0.23, 0.49. Okay. So that is corresponding to minus 0.23 and minus 0.49. And other one corresponds to minus 0.38, 0.30. Okay, so that is my phi 2, that is my phi 1, this is my omega 1, this is my omega 2. Okay, I think this is omega 1 square. Omega 1 square, na? Yeah, this is omega 1 square, omega 2 square, and this is a cylinder. Okay. Now we see that in the last case, that once we are taking both the system and solve it, fantastically we are getting the result. That's getting the complete response. Means what we do, we like go like this way, that we are having the full matrix, that is U1 equal to Q into this. So maybe I'll just write it again. That is my U1, U2 will be equal to phi 1 times Q1 plus phi 2 times Q2. Okay, and we mentioned that let's assume this is my u1 axis, this is my u2 axis. So we are revolving somewhat and we are going, this is q1 axis, this is q2 axis, and we are measuring this, the method, sorry, maybe I just draw it in the other color. So like it is movement in this axis and this axis, and from here we are able to like get some sort of like a motion, and that we are again transferring back to u1, and we try to see that how the responses are coming. Now if we are not considering that q2, then what are we doing? Because that is the case what we just discussed. Like let's say we are analyzing a 100-storied building, we found that our mass participation is coming 95% in like first 5 mode. So we just forget like remaining 95 modes. We're just taking only the first 5 mode. So that is something similar case. I'm not, obviously I cannot write a 100 thing and able to draw that. So I'm just trying to thinking it like, okay, if we are having a 2-degree freedom system, and instead of taking the 2 modes, if I just take only a single mode, what exactly we are solving? Okay, or how close are we going? So first 2 things we need to check. One thing is that try to check what is the mass participation ratio and what is the modal participation factor. Both the thing, let's try to check. First is the mass participation. So ME, if we try to calculate, that is phi1 into mass into R divided by phi1, sorry, transpose M into phi1. This is whole square. Okay, maybe I'll do it quickly over the MATLAB. Yeah, if I just run it also, I will get the model. So mass normalized mode shapes. Okay, just copy that. Okay, so I have that mode shapes with me. So I have the first 2 modes. So maybe I just say phi1 is nothing but the mode first column I'm taking, then phi2 will be equal to mode in second column. Okay, okay, makes sense. So this is my 2 modes. Okay, 2 modes I am getting. Now I try to do that phi1 transpose this one is that. Okay, phi1 transpose into M into, there will be a R matrix. So R will be equal to once 2, 1 into R. Okay, so that is just saying mm, it will be equal to this one square divided by phi 1 transpose into M into phi 1. Okay, so that is my M1, and my M2 will be similar manner. I will just do it for phi 2. Yes, instead of 1, I'll do 2. I need also the M matrix, otherwise it will not solve. M matrix is, I think that was again same. Just need to check whether like we are doing the same problem. Yeah, 5 3 0 0. So 5 0 0 3. Okay, done. So now let's see. That is MDOF model mass. Yes. Now you see, no, sorry, both the cases I wrongly put M1, M1, M2. So now you see that first mode, the mass is coming 6.98. You can see that 6.98, and second one is coming 1.01. We were expecting something in the 100% or something 0.95. What happened? So what is the problem? Divide by the total. Divide by the total mass. That we have to do. We have not done that, so don't worry. So yeah, so now if we just divide it by the total mass, so total mass is how much? 8. 5 and 3. Total is 8. I just divide it normally. Nothing special. Close that. Good Baba. Yes. So you see, first mode is going for 87%. At second mode is going for only for the 12%. So we are mostly okay. Like first mode means as per this theory, we are okay. That if we just only consider the first mode, now let's see what happened. Okay. How much we are neglecting or what exactly happening? Yes. So from here, we identify that our first one is coming approximately equal to 87.5%, and M2 is coming approximately equal to 12.5%. Mostly like that. Okay, good. And here, if you see, like as I told in the last case, once we were doing, we had like phi 1 equal to phi 1 transpose M, then that one is no, that with something, yeah, current transpose. So that was my M1 that is equal to, yeah. So suppose if I just say that phi M1 that is, or gamma M1, G M1 that is equal to this one divided by GM2 equal to, let's write it. So you see, one is coming like 87.5 around, and that is coming 12.5 around, and this is coming minus 2.64, and another is coming minus 1 participation. So that is telling whatever the direction you are giving the force, you should take in the equivalent single degree freedom system with that phi 1 should be opposite, because that phi itself has negative value. So you have to use the negative sign. with the Q1. Okay. Yeah, just let me. So minus 0.264 and that is minus 1, around minus 2.6, and this is coming around minus 1. Okay. Now let's see, we are having a force, or maybe we are just giving a base excited motion in that same thing. So my equation will be how much if we are giving a base excited motion in that? That will be remain exactly same as it was, because that is not going to change your original matrix. Here you will have 5 3 1 1 UG double dot. Agreed? Agreed, all of you? Just similar way, I just try to write it so that actually means that you are now having here the UG double dot excitation. You are just displacing your base with UG double dot excitation. Okay. Now here, and if you see that our expression previous case, it should be like, once you are solving that, so we have just go to the Q system. So in that Q system, your first equation is Q1 double dot plus 8.8 into Q1 should be equal to how much? 8.8 Q1. If you just go back to the last equation, last time, if you see, Q1 equal to this portion, Q1 equal to 8.8 Q1 equal to 0. There was force free vibration, that's why it was 0. Now it is force vibration, so there should be the force component. But we have already mentioned that F1, F2, F3, whatever is force is coming, and these force are not same, because that is a rotated coordinate already. So that force you have to also calculate that what type of forces will be there, and also the next equation you have also seen. So these two equation will be also remain same, because Q2 double dot plus 37 point, how much? 37.8 Q2, that will be now the important point, how it should be. So first let's see how it was. If I just do that calculation, so it was basically, so we had, this is something like phi transpose F, okay, divided by, like this is phi transpose F divided by that is phi 1 transpose M phi 1 transpose. That is actually phi 1 transpose, yeah. So phi 1 transpose F. So what was F here? F is actually nothing but 5 and 3. The 5 and 3. Okay. So that 5 and 3, and you are multiplying with the UG double dot, obviously. But UG double dot is just varying with the time. That is same way it will vary. Not a problem. Now, if you just multiplying with the phi 1 transpose, that means phi 1 transpose is your minus 0.23 minus 0.49. You are multiplying this one with like minus 5 minus 3. The first thing is that minus will be vanished. So this into this, minus 0.23 into, so 0.23 into 0.5, sorry, 0.23 into 5 plus 0.49 into 3. I did not write all the terms. Did you see that? This is also 2.62. So you can just place here 2.62. So that means whatever is the modal participation factor, modal participation, not mass participation, modal participation factor is coming, that is telling phi transpose F divided by, and that is the definition of it. So it must be equal. Why not? With UG double dot perfect. And the next one will be how much? That will be 1 into UG double dot, because you have to see here we have a minus sign and here we have a minus sign, so that two minus is get cancelled out, and therefore we are not having the minus. Otherwise your mass matrix will not be minus, na? Means if you see here once I considered that minus sign, so that's why this anomaly is happening. Okay, otherwise there will be no minus sign. Okay, so we will have this one. Any doubt? So this tells what? The response of this system is much higher compared to the response of this system. Can I say it? I could say, I could not say. That depends on, because why I am saying that I could say or could not say, because it is not a response of a static system. Suppose instead of an earthquake motion, which is like some type of spectrum, like suppose if you are giving a harmonic excitation, it can be also harmonic excitation, not a problem, because it is UG. I am not defining anything. It can be a harmonic excitation also. So now if you are having a harmonic excitation which is close to like root over of 8.8, then this system will go in resonance. Obviously, because that peak will be close. Means if I try to see that in the frequency domain plot, this one will be like this way, that will be also like this way, but these two frequencies are different. Like one frequency is like this, and another, if I draw this one, that will go like this way. So this case, this is root over of 8.8 and this is root over of 37.8. These are these two peaks. Okay, and you see whatever is your UG, that is multiplied by 2.26 times for the first case, and in second case it is only multiplied by 1 time. And if you go further, maybe you will see it is more reduced. It will be not even that much. But although in this case we do not have more, so it is less. So that way, actually, now if you can think that, okay, if your system is lying somewhere close to this frequency, the contribution of this will be very high compared to the other one. We need to understand also, like, okay, where and which position, if we are approximating, I will be correct. I will also try to draw it in a much better manner so that we can able to. Please remember that equation. That is Q1 double dot plus 8.8 Q1 equal to 2.6 UG double dot, and other one is Q2 double dot plus 37.8 Q2 equal to 1 UG double dot. Okay, now if I just try to see it, the first case it will go like that. We will have the diagram like this, which is the dynamic amplification factor diagram, if you remember. Then second case it will go first case, this one is how much? Root of 8.8 and this is root of 37.8. Now this is getting multiplied by 2.6 times. So this graph is go somewhere here. This will go like, sorry, this will go like this way, and this will also go like this way, 2.6 times more. So now you see that, although means I don't know whether it is 2.6 times, I can able to draw it or not, Well, like you can see that if it should start from 1, it will start from 2.6. First of all, there is a two things. We cannot directly add this up in this diagram. If we draw it like this way, we can add them up, because this drawing is generally in the log scale. So log scale we cannot directly add. We have to go to the normal scale and we can add. Okay, but if we try to see that the differences is where, like this much is the contribution of the first mode, second one, and this is the contribution of the first. Previously I just mentioned that is the contribution only. No, that's the full thing is the contribution. So you see that this is mode, like, but if we go here, then we see the contribution of the second is more compared to the contribution of the first. Agreed? That point? Obviously. Now, if you try to think that where is that problem? So, we are very good to predict from the first equation only. Now, our question was that if we just take only the first equation, where are we? So if we think that if we are taking only the first equation, means this one, this we are not considering, because we try to reducing that scale. So we are not considering the one equation. We are just happy ourselves with the 87% mass, not 100%. So we are good once we are not reaching close to the natural frequency of the second system. Okay, means we are good in the near the first mode's natural frequency, means the first mode. But if we are getting close to the second mode, then your error will start increasing. So that you have to be very sure. Means you are okay to truncate the modes, but you have to also see where you are lying.
It's opposite direction.
Modes are opposite direction. Yes.
So response of one mode negative to another.
Negative to another mode. Yeah. That is also another important point. Yeah, that I also missed. Perfect point. Yeah, because we are doing it like phi 1 q1 plus phi 2 q2. That phi is also contributing here. So now if you see that first case phi is this much and second case phi is this much. So for the first mass, you see what I told is more or less okay type thing, but in the second one, phi 2 will be negative. So they are actually like subtracting that one exactly. So like this way, more or less like we can try to plot both the diagrams and try to see that where it is the contribution coming. But in general, what we can able to see that if you are neglecting some modes, the near the natural frequency of those mode, your error could increase. Okay, because in those ports, like here also, like if you see that this will try to go to infinite, na? So that response itself is quite high. So that is actually the scenario. So any doubt up to that? But most of the cases, now if you come into that, so are we doing okay with the earthquake case, that we are not considering the higher modes? Now if you see, earthquake is not a harmonic excitation, rather it's a band of excitation. And we are not making any harmonic like it's a sine omega t. No, it's not a sine omega t only. It is combination of the several signs. Means if you do the FFT of it, like a Fourier transform, you can able to see like how the spectrum is coming actually. Okay, so it's generally, if you take a earthquake signal and you do FFT, you will found that the frequencies are lying between 0.5 to 20 Hertz. That's the range more or less your frequencies are down. Now, in what range your building's frequencies are lying? We are, first of all, we are working in the time period. So time period is the 1 by frequency in the Hertz scale. So, and if I just very roughly think that suppose we have a five-story building, frequency time period will be around 0.5 second. Basic thumb rule, that's the 0.1 second for each story. So around 10.5 second. 0.5 second means 2 hertz. 1 by this is a 2 hertz. Now if we are going like little taller, like let's say 10 storied, it will become 1. So your frequency will become 1 hertz. 1 second, 1 hertz, simple. If you go for the 20 storied building, it will go somewhat around 2 second time period. Frequency will be somewhat 0.5 hertz. But although these are not exactly value, but these are very thumb rule. But you will get it mostly closer. But that is the frequency of the bare frame, not the infilled wall. Infilled wall, it will be time period, I think, will be lesser side. It will become more stiffer mostly. Although you are adding some masses, but still the joint stiffness and all those things will be increased. Yeah, so that way the things happens. So now if you see, higher modes means your frequencies will be higher, and what we told, that is the first mode's frequency. There will be second mode, third mode, fourth mode. So frequency will be higher side, because we take the highest time period and then second highest time period, like this way. But once we are talking in terms of frequency, we are taking lowest frequency, then second lowest, third lowest, like this, ascending order. And but in case of time period, it is descending order. Okay, so you will see that most of the cases, like after few modes, your frequency will be very high, because time period will be reduced. So that will go out of the 0.5 range, and there will be no chances of the resonance. So that's why you are safe, no problem. Otherwise, we have to do it for 100 modes, and like we will just put it, and maybe one day or 2 days will be gone for designing. Okay, so that way the things is happening. I think you got a understanding what is going on. So now let's try to focus little bit on the response spectrum point of view. Like suppose, and try to do a problem related to the building, like we have a 5-story building problem, and try to see how it is going. Yes, so the building is, let's say you have a 5-story building. The mass of the floor, so each mass is 3000 kg, 1. All the floor masses are same, and that is every mass is 3000 kg. Very simple. And stiffness in each floor, that is also same, that is 10 to the power 8 Newton per meter. Okay, all stiffness are same. So what should be the mass matrix? Assume like this is 1, 2, 3, 4, 5. That is generally the way how we write, because 1 automatically denotes the first floor, second floor, third floor, like this way. Okay, some people do it reverse also, but that, like, you have to again subtract. Okay, so that I found quite better, like do it properly. Okay, so now if you do it, then what happened? How to do the mass matrix, please, anybody? Simple, 3000, 1. Done, nothing big deal. How to do the stiffness matrix? 10 to the power 8, then there will be 2, -1, -1, 1, 2, -1, -1, 2, -1, -1, 2, -1, -1, 1. How many? Yeah. So this is that easy to write the stiffness matrix. If you literally follow that way, how to write mass matrix, stiffness matrix, that this can be done like in few seconds. you can able to write your stiffness matrix. Okay, so now mass matrix, stiffness matrix is done. What the next thing to do? First thing is the natural frequency. Try to calculate what are the frequencies, eigenfrequencies. So frequencies, if I try to calculate, that will be coming somewhat to 29, 57, 179, 94,000. So big numbers. This is omega square. So that's why it is coming big. But yeah, so if you see the omega, that will be 52, around 52, 152 to 39, 239, 307 and 350. So this is in the rad per sec. Okay. So if I see the time period coming 0.12, 0.04, 0.0269, 0204 something and 017, that will be in second. So we see that time period also get way off. Okay, and this is not any real building also, it's just like we just take some help. So now I will try to show that okay, that is my matrices come. Now what I am trying to just take only the first two modes. I'm not going to consider all the 5 modes. Now it will give 5 modes, but I am taking only the 2 modes. Okay, so if I take only the 2 modes, and I also have like a phi 1 matrix, phi 2 matrix like this. So my phi 1 matrix is coming somewhat 0.285, 0.546, 0.764, 0.91 and 1. That is my first matrix. I mean the first mode shape. First mode shape corresponding to time period of 0.12 second and frequency of 52 hertz, and that's 52 radian per second. Okay, so that is the scenario. Now I can also see that modal participation factor of this one is 1.62. So that means, and also maybe I can do the phi 2. Phi 2 is 0.764, 1, 0.545 minus 0.285 and minus 0.918. That is my second mode. And second mode time period is getting 0.04 second. Frequency is 152 rad per sec, and gamma 2 will be 0.39. Okay, so in the first mode, what can we see? Like we can see that the first mass, means if I just try to draw it, that fifth mass is somewhat in the 1, then second mass is 0.91, third one is 0.76, this one is 0.54 and this one is 0.58. So you will get more or less like this type of graph, or rather it is more like this. Okay, because the variation in the top is less compared to the variation in the bottom. Because top, if you see, it is 0.9121, then 0.75 to 0.91. So variation in the top is less compared to the variation in the bottom. In first floor, first variation is almost 0.28. Means in one floor it is 0.28. Then second floor, if you see the variation, 0.28 to 0.54. That is somewhat again 0.25 range. But then the top one, no, sorry, yeah, 5.4 range, then 5.4 to 7.6, and then 7.6 to 9, that is 0.15 range, and that is in the 0.1 range. So the top portion is slow there. So this type of graph you can able to expect that. So this is my mode shape of my first mode. And what about the second one? Second one, you see, it is 1.76. So we can try to draw it with the other color, maybe. So that is 1, no, not 1. This is 0.6. Then it goes to 1. So this, then it goes to 0.5 somewhere here. Then it goes to minus here. Then here, here. So like this one. I'm sorry. Little mistake, huh? Yeah, it should be like that. So first one is negative 0.91 minus, then 28 somewhere here, then 543 somewhere here, then 1, then 76. So the next one will go like this. Okay. Most important thing, the characteristics. First mode shape never cuts the axis. Second mode shape cuts one. So this is matching. So good. Now the question is that, okay, this thing match, nice. Now how do we going to use that? If you see, once we are doing the seismic analysis, we have response spectrum. Although we have to study what is the response spectrum and how that thing came and all those things. But just like assume that we have the response spectrum, so this goes like this. That's like a typical curve. Okay. And this is SAYG. Although we have to study that complete thoroughly, means just like first we are just taking it as it is given in the code and we'll try to find it. Now think that you are getting a time period that is 0.12 second. So what you can do, you can just pick the point corresponding to 0.12 second. So whatever the SAYG is coming, you are picking it up. So you can say that that is my SAYG. Fantastic. And that SAYG you can multiply with the modal participation factor. That whatever the factor is coming, so then it will tells you that how much is actually coming on that. Okay. So like this way we have to actually go with that, because for this first I have to teach what is the response spectrum, because there is some other things also like the HD displacement calculation and those things. So that thing I cannot tell without teaching that. So maybe in the next class I will first go for the response spectrum calculation, and then we will see the remaining part, that how it is actually we can able to use that.